Now let us see an interesting application of the transition state theory rate expression that we already derived. So we have to calculate the partition functions to derive any expression for a particular say bimolecular reaction. So in order to see that this expression is actually equivalent to our collision theory expression, let us proceed. And here what I have drawn is basically just to give you a feeling of what we are talking about. So remember that we have suppose a bimolecular reaction between two atoms or molecules, and these atoms and molecules we are approximating A and B denoted the atoms or the molecules, and then we are approximating this shape of these atoms or molecules to be spherical, and these are hard spheres in the sense that if I plot the potential energy between them as a function of the distance between them. So as soon as so the potential will be 0, but as soon as these two atoms or two molecules touch, the potential energy goes to infinity, and that happens when that center to center distance is basically the addition of the radius Ra plus Rb, which we call as B max. So B is usually in the scattering theory is defined as an quantity called impact parameter, and so it is defined as, suppose I have one atom or molecule which is a sphere, and then the other one is approaching at a angle something like this, and then you will see that center to center distance actually varies, in the sense that we could have many different possibilities, like this can go like this, and suppose the atom A is in stationary position. We are actually denoting the atom B as the bigger one as atom B. So let us stick to that convention, and this is A. Now if A comes like this, then we can actually have, after some time, A is just touching the B. So that is the maximum position of the impact parameter, in the sense the center to center distance is just as addition of Ra plus Rb. However, we can have another possibility that A is coming like this, and then when they collide, as you can see from this picture, the center to center distance is now less than the B max, or less than the sum over radius of the two atoms. And you can also have a head on collision, like A is coming towards B, and then as it approaches, then it just has an head on collision, and that time the center to center vertical distance is basically 0. So this B can be can take values between 0 and B max, and this B max is very important in collision theory, because we know that if the atom A or the molecule A lies within a distance B max from the center of the other molecule or atom, then the collision will happen, which is very clear from this picture. Now in collision theory we use this B max, and then we get a rate expression, something like if we write it as KCT is basically a collisional cross section, which is pi B max squared. So which sometimes we write it as sigma, the collisional cross section, times the average of relative velocities. Now what is the average of relative velocity? I will come to that, and times some energy, which is basically equivalent to the minimum energy requirement in Arrhenius. It's not exactly the same energy as we see in Arrhenius expression. Remember that Arrhenius expression was K is basically A into e to the power minus Ea by RT. Now that Ea is slightly different, because that is actually a measured Ea. So it is basically the energy Arrhenius found through experiments, that the minimum energy that is required, and he interpreted it as the minimum energy. But although it's basically when we do the experiment, it is done on a statistical ensemble of atoms or molecules which are undergoing the reaction. So this EA, capital EA, is kind of an average energy. Now what we are talking about right now, E star, is basically from a very quantum mechanical point of view, where we have a potential energy surface, something like we draw earlier. So here EA has a meaning of, E star has a meaning of like this. So it is basically the energy difference between the 0 point energy and the 0 point energy of the transition state. Something like that we have in mind. And then what we are saying is that that expression will basically the E star, or the minimum energy expression, will go as a Boltzmann factor, which we derived in the earlier course in thermodynamics and kinetics, which you can also see in your the recommended text. And then you have another term, which is the relative of the average of the relative velocities. Now what is average of relative velocities? Now as we just said, that the approach of A towards B, if we think that B is stationary because everything is in a relative frame, it can be many ways. So in this picture, where we showed that these two are having a head-on collision, in that case the angle of approach is basically 180 degree, because as you know that B is moving in this way, A is moving in this way, so the relative velocity will be added up. So in that case the V relative will be VA plus VB. Similarly, the relative velocities can be also at 90 degrees. Like atom B can move like this, atom A can move like this. So the approach is there 90 degree. And then you can have also in between situation, like atom B is moving in this direction, but A is moving like this, which means actually if I think about all these angles, like from 0 degree to a maximum of say 180 degree, so anyway, so we have to think about the relative orientation of the relative angle. As you can see that at a 90 degree there will be no collision because the vector by virtue of vector addition, we will see that these vectors are orthogonal. So what we can argue from here is that if we want to calculate the relative velocity, that then we have to think that as if these two things are colliding but at 45 degree to each other, and then we have to take the relative velocity component. So which means actually you have to take the, if I have say a head-on collision, like we add up, but this adding up comes basically from cosine of 0 degree, because we have a 0 degree collision here. But if we have a 45 degree collision, then, and if the atoms are of same type, so then I have to take just the relative velocity as not V plus V, which is 2V if the atoms are or the molecules are same, but I have to take V into cos theta, where cos theta is 45 degree. So I will have basically root 2 into V. Now you know that there is a relative average velocity expression. If the average velocity expression is basically comes from Maxwell-Boltzmann distribution of molecular speed, I should not call it as a velocity, it is basically average speed. Now that expression has a form something like this. It is 8 kBt by pi m raised to the half. So it's it basically comes from, you can easily calculate how to find out this average velocity. You have to just take the velocity, and since you are calculating an average, you have to take multiply it with the probability distribution, which is the three-dimensional Maxwell-Boltzmann distribution for molecular speed, and then you have to integrate over all possible speed, and that will give you this value 8 kBt by pi m. Now if I have actually this kind of situation, square root of 2v, then it can be easily shown that for a relative velocity we can write a similar expression, but it will be nothing but 8 kBt by pi mu, where mu is basically the reduced mass of the system, where mu is nothing but ma mb by ma plus mb. So we can easily formulate that. It's very easy to show. Now coming back, so this is basically a collision theory rate expression. Now if for this is true for any two structureless atoms or molecules, or the collision between them, which is a bimolecular collision, The same expression we should also get from the transition state theory. But for the time being, as you can see, that the expression which we have got from transition state theory is rather much complicated, and it actually involves the partition functions. But we can show that for atom diatom or any collision like this, we can actually show that for structureless systems, where actually we can think that initially the atoms or the molecules which are participating in the reaction has only translational degree of freedom, then the two theories are very much equivalent. And remember that you may think that it is not equivalent for a complicated molecule which is large enough, and where actually we have lot of initial vibrations and initial rotations. But you have to also remember that the collision theory model which we just discussed is also a very simple model, because that is also dependent on the Hertz sphere model. So this model applies to Hertz sphere, and we got an expression. So the logic is that for Hertz sphere, that kind of model, the transition state theory also should give us a similar expression. Now there are also modified version of collision theory, or which is known generally known as the scattering theory, but those we are not going to discuss. I mean, there actually you can calculate the scattering cross section from either classical mechanics, or actually talk about scattering potential, and then talk about a deflection angle. From that you can calculate the scattering cross section, and then you can incorporate the quantum effects very intelligently to it, to again modify the expression for the cross section, and then you can actually calculate the rate constant. But we are not going into the details, and those detailed calculation now show exact similarity with or near exact similarity with the transition state theory, even for polyatomic molecules. Now coming back to our discussion, we have to calculate the partition functions, and remember I'll just write the partition functions once again just to remind you. So you can actually go back and have your note where we discussed the statistical thermodynamics, and we calculated the molecular partition functions for different degrees of freedom, translation, rotation, and vibration. So, and electronic partition function, we said that we always take it to be 1. So instead of Z notation, I will be using our old notation, which is the Q notation. So we know that Q translation, and usually the translational partition function is expressed per volume, and that's why if you see here that for both the transition state as well as the reactants, we have written per volume, partition function per volume, but this volume part gets associated with the translational part. So Q translation is nothing divided by volume. If you remember that it will be 2 pi m kBT divided by h bar squared, and if it is a 3-dimensional problem, we will have 3 by 2, and there is a L in the translational partition function expression, and that L cube gets transformed into V, and that's what we have done. Basically we have divided the translational partition function divided by V, and then so this translational partition function per unit volume. And then similarly we can have the rotational partition function, and that is 8 pi square I kBT divided by h square into sigma. Now sigma is basically the symmetry number. In this case, if we assume that A and B are different, then we don't need to actually consider any sigma for here, but for homonuclear diatomic molecule, for example, we have to choose sigma to be equal to 1. The reason is per half rotation it basically creates exactly the same structure, and you can easily visualize it. Like if I have a H2 molecule, for example, so if I just rotate it by 180 degree, so not by 360 degree, we'll see a similar structure, and that actually has a much deeper consequence in terms of the symmetry of the molecule and how it is connected to the energy levels of the molecule. And we can actually figure out that there are basically the rotational quantum states can be split into two ways, which are basically the odd J states and the even J states, and one corresponds to the something known as orthohydrogen and another corresponds to the parahydrogen, and it depends on the nuclear spin permutation. So we are not going into the details. You can actually get all these details in your Atkins physical chemistry textbook, which is one of the textbook recommended to you. And there is a chapter on statistical thermodynamics, and you can actually look up there, and you will get a fairly good explanation of this symmetry principle, how it is applied to the spectroscopic lines or the number of degeneracies for the rotational transition. Now, for our case actually, so as we said that symmetry number is not necessary, we just take it to be 1. And similarly, we also have Q vibration, which we already know that Q vibration for any particular vibrational mode will be 1 divided by 1 minus e to the power minus h nu by kBt, but that is for the nth mode. So we should actually write it as a subscript as nu. And then the electronic partition function, we are usually using it to be, taking it to be 1. Thinking that it's all the reactions are happening in the ground electronic state, because if you remember the potential energy surface, that the reactants are basically promoted, so there are vibrational levels, so there the reactants do some translation and vibration, and they are now promoted to an energy level, so that actually they can acquire a configuration of a transition state, and such that they can now react. So that promotion gives the necessary activation energy and necessary geometry also, and when they are promoted, that reaction will basically occur, but everything is happening in the ground state potential energy surface. It's not like that we are basically doing a photochemistry where actually we are going to the excited state and doing the reaction. In that case, partition function may change because the reaction is happening in a different electronic surface, which can be, for example, a triplet state, and in that case I have to take it to be Q electronic to be 3. So in general, if we do not have too many complications of the atoms or the molecules which are reactants, we can actually take the electronic partition function to be equal to 1, because most of the molecules also, the ground electronic states, all the electrons are paired and it's a singlet state. So now we can proceed, and then we can figure out what will be the expression for an bimolecular reaction, what is the transition state theory expression for the rate constant for a bimolecular reaction. And first thing first, we have Q AB dagger. We can actually look up, we don't know to remember it. So it's kBt divided by H. Let me write it. So we have kBt divided by H times, we have translational partition function of the transition state divided by volume. Now the transition state, the way we are thinking right now is basically a bimolecular reaction. So the transition state in this case, which is a bimolecular reaction, will look like something like this, where we denoted it as A and this is as B. So it basically has many degrees of freedom. It has 3 translation, 1 vibration along the internuclear axis of these 2 hard spheres, and then it has rotations, but it is a linear transition state, so it will have 2 rotational degrees of freedom. And if you remember that the rotational partition function which we wrote, that is basically for 1 degree of freedom. For 2 degrees of freedom we have to modify it accordingly, and then it has 1 particular vibration, and that vibration we can think that it is the reaction coordinate. Although this is not very correct thing, because you can imagine that I have a hard sphere atom or molecule A, and I have another hard sphere atom and molecule B, and they are forming the transition state, and there is some vibration I am saying, but it is not exactly the vibration along AB, because that vibration will not give you reaction, because it will just give a reaction where A and B are apart. So what we are saying is that it's a linear thing, and there is some particular vibration that is giving me the reaction of the type A plus B is giving me product. So that vibration we are basically isolating, and that vibration is basically already less in the expression for the Q AB dagger by phi, and we have a prime notation there, and remember that is basically the prime takes into account of the fact that 1 degree of freedom is less, and we are saying that particular degree of freedom is the inherent vibration which is leading to the reaction. So now we can proceed. Now we see that the expression will be the first Q AB dagger divided by V. So it has its translational partition function which will be 2 pi m. Now if the mass of A is Ma and mass of B is Mb, so the as we can see, the mass of the transition state will be Ma plus Mb, because it will be the total mass is conserved, divided by h square, which is a Planck constant, raised to 3 by 2. That is the Q translation divided by V for the transition state, times I now have to write the rotational partition function, and the rotational partition function in this case will be 2I kBt by h bar squared, but we probably wrote the rotational partition function in terms of h, so we can actually, instead of writing h bar, we can write it as h square, and h bar is h by 2 pi. So in the numerator we'll have 8 pi square I. We can use any of this expression, and then this is for a linear molecule, so that's why we had a sigma here, and sigma is basically 1. And then what we have is 8 pi square I kBt by h square, and then the vibrational, but the vibration we have already taken into account, and then you have electronic, which is just 1. So remember that since we have taken out the vibrational degree of freedom, that's why it is giving the kBt by h, that expression. And now I have the Q vibration partition functions per unit volume for the reactants. So first I'll write it for A. Now A has only translation and B also has a translation, because these are structureless atoms or molecules, the reactants. So for A we can write it as 2 pi Ma kBt divided by h square raised to the power 3 by 2, and for B we can write 2 pi kBt 2 pi Mb kBt divided by h square raised to the power 3 by 2. And then in the overall expression we also have a Boltzmann factor, so where the factor looks like e to the power minus epsilon star by kBt, and epsilon star is the 0-point energy difference between the transition state and the ground state for the composite ground state of the reactants. Now as we have to just simplify this expression, as you can see here that this 2 pi kBt divided by h square, one of them will basically cancel with one of them in the numerator 2 pi kBt by h square, that factor will cancel with one of them. Let's say this gets cancelled with this, so I can actually use some other color. So I'm saying that that is getting cancelled, and then I am left with something like 2 pi kBt by h square in the denominator, plus I have here Ma, Mb and Ma plus Mb. Now those things we can actually arrange, and we see here that is nothing but 1 divided by Ma Mb by Ma plus Mb raised to the power 3 by 2. So that is nothing but the reduced mass, as it follows from the expression from the reduced mass. So this is nothing but 1 divided by mu to the power 3 by 2. Now this I is basically moment of inertia, and for this I of the transition state, if we think that the distance is we already denoted it as B max, so the moment of inertia is nothing but mu B max squared. So we will replace that I as mu B max squared, and then what we are left with that this mu, as you can see, will basically cancel with the mu to the power 3 by 2 in the denominator. So ultimately we will have a mu to the power half in the denominator, and then you can also simplify with the other terms. You can actually quickly try doing that. So we will have 1 kBt by h times, we will have I am writing the rotational partition function first, 8 pi square will have kBt divided by h square, and I am writing as mu Bmax squared. That was the rotational partition function. And then I have 1 over mu to the power 3 by 2, and times in the denominator I have 2 kBt divided by h square raised to the power 3 by 2. So that I can write it as h square. In the above I can actually write it as h square, and then I have 2 pi kBt raised to the power 3 by 2. So now let us now look at it, like what gets cancelled with each other. First thing first, this mu gets cancelled with mu to the power 3 by 2. So I'll have mu half here, and then what we are left with is let us first look at the h. So I have h here, I have h here, h square here. So I have h cube, and then I have h squared to the power 3 by 2. So that is also h cube. So these things actually gets cancelled with each other. And then all I am left with is 2 pi kBt here, and I also have 8 here, but remember that that is raised to 3 by 2. So let us look at the kBt terms first. So I have kBt here, I have kBt here, so I have overall kBt squared, and then in the denominator I have kBt to the power 3 by 2. So kBt squared, you can think of it as kBt to the power 4 by 2, and divided by I have kBt to the power 3 by 2. So that will give me basically 1 over, not 1 over, that will give me basically kBt to the power half. So these things will get cancelled with this kBt, and in the numerator I will have kBt to the power half. And let us now look at the pi's. So I have pi square here, and I have pi to the power 3 by 2. Now I'll just do a simple trick. What I'm going to do here is that out of this pi square, I will actually keep one of the pi and associate with the Bmax. So what I'm doing here is that I had one pi here. I'm basically writing this pi square as pi into pi, and that one pi I'm associating with this Bmax. So basically I have pi Bmax squared, because I'll show the equivalence of the transition state theory and the collision theory expression, and I have a pi Bmax squared here, as you can see here. Now then what I have is, remember that I also have e to the power minus e star by kBt, that I'll not touch. So I'll have 1 e to the power minus e star by kBt, and then let us have a look what we are left with. So we are left with 1 pi here, and so we have 1 pi. Let me use the different colors. So we have 1 pi in the numerator, and in the denominator we have pi to the power 3 by 2. So that pi we can write it as pi to the power 2 by 2. So we'll have overall 1 over pi to the power half in the denominator. So again, so this pi and one of this pi will get cancelled, and then I will have pi to the power half in the denominator. And let us now look at the numbers. Like I have 2 here, 2 to the power 3 by 2, I have 8 here. So we can also have a look how it goes. So I have 8 divided by 2 to the power 3 by 2. So 2 to the power 3 by 2 is basically 8 to the power half. So overall I'll have 1 over, not 1 over, I have basically 8 divided by square root of 8. So I'll have square root of 8, or 8 to the power half. So this thing will get cancelled with this, and I'll have 8 to the power half. So now I can actually arrange the terms, and as I can see here, so I have 1 h to the power half, I have 1 kBt to the power half, and then I have 1 mu to the power half and pi to the power half. So I'll just arrange all of them, and then I can write it. In the numerator I have 8, kBt, and the denominator I have pi mu everything raised to the power half. And as you can see that this is exactly the expression for the relative average velocity, which we have already figured out, and that will be basically when the relative collision between A and B happens at an angle which is basically average of 0 and 90 degree, so which is basically the 45 degree. Now as you can see that now we have actually got back our collision theory rate expression, that I have pi b max squared, and then I have 8 kBt by pi mu raised to the power half, is an average of the relative velocities, and times this Boltzmann factor. So now we see that we can easily show that kTst is equivalent to kCt, or the collision theory, if we think that the reaction is happening due to collision, due to bimolecular collision between two structureless atoms or molecules. So this basically shows the equivalence of the two methods. Although at a first look, the collision theory rate expression and the transition theory rate expression looks very different, but we see that for structureless atoms and molecules and the bimolecular reaction between them, these two are very much equivalent. So now we'll see the thermodynamic aspect of the transition state theory.